There is a method that costs about $2. Not a premium oil change. Not a high-end synthetic upgrade. Not a dealership engine protection package. $2. And when used correctly, it can dramatically reduce internal engine wear and extend engine life far beyond what most drivers think is possible. Not by a small margin, not by 10 or 20,000 miles, but to the point where engines routinely reach 400, even 500,000 miles without internal failure. Japanese mechanics have been using this method quietly for decades. And the reason you've never heard of it has nothing to do with whether it works. It works extremely well. In the US and Europe, engine lifespan is treated as predictable, 100,000 miles, maybe 150 if maintenance is good. After that, wear accumulates, clearances increase, efficiency drops, failures begin. That's considered normal. Entire service models are built around that assumption. Oil changes every 10,000 miles, component replacements at fixed intervals, eventually major repairs or engine replacement. But in Japan, the exact same engines, same blocks, same machining tolerances, same suppliers, routinely operate at 2, 3, even 4 times that lifespan. Same engine, different outcome. They didn't redesign the engine. They didn't use exotic materials. They changed how the engine is protected. And once you understand how, you'll start to see something most drivers never question. Engine wear is not just a function of time. It's a function of lubrication failure. Because inside your engine, metal parts are moving at extreme speeds. Crankshaft bearings spinning thousands of times per minute. Cam lobes sliding against followers, pistons traveling up and down the cylinder walls. And ideally, none of these surfaces ever touch. They are separated by a thin oil film. This is called hydrodynamic lubrication. As long as that oil film is intact, wear is minimal. But real-world driving doesn't operate under ideal conditions. Cold starts. When oil hasn't fully circulated yet, when viscosity is higher, when surfaces are not fully separated, high load conditions, where pressure exceeds the oil film's ability to maintain separation, high temperatures, where oil thins out and loses protective capacity. During these moments, the oil film breaks down, and when it does, metal contacts metal. Not enough to cause immediate failure, but enough to create microscopic wear. Tiny particles are removed, surface smoothness degrades, clearances begin to change, and over tens of thousands of cycles, that microscopic wear becomes measurable, then noticeable, then expensive. In Western maintenance models, the response is simple. Use better oil, change it more often. Maybe add a cleaning additive, but the underlying assumption remains unchanged. That oil alone is responsible for protection, and that occasional metal contact is unavoidable. Japanese engineers approached this differently. They asked a more fundamental question. What if oil wasn't the only line of defense? What if you could create a secondary protection layer that remains even when oil fails? And that's where this compound comes in, molybdenum disulfide, also known as MOS2. This is not a marketing invention. It has been used in aerospace, heavy industry, and high-performance engineering for decades because of one specific property. At the molecular level, molybdenum disulfide forms a layered crystal structure. These layers slide over each other with extremely low friction. When introduced into an engine, MOS2 particles bond to metal surfaces. They don't just float in the oil, they attach, forming a microscopic solid lubricant layer directly on the metal. And this layer behaves very differently from oil. Oil relies on pressure and flow to maintain separation. MOS2 does not. It remains in place even under extreme pressure, even when oil film is temporarily lost, even during cold starts. That means that during the exact moments when most engine wear occurs, there is still a protective barrier present. Not liquid, solid, stable, and extremely low friction. This changes the wear dynamic completely. Instead of metal contacting metal, metal contacts a lubricating layer, and the difference over time is enormous. Japanese manufacturers and service networks have understood this principle for decades. While they may not openly advertise it, molybdenum compounds have been integrated into lubrication strategies in various forms: factory oils, assembly lubes, service practices. But in many Western markets, the concentration of these compounds in standard oils is minimal, because high concentrations reduce wear too effectively. And that creates a problem for an industry built around predictable degradation. Think about how many services depend on wear: engine rebuilds, bearing replacements, camshaft wear repairs, increased oil consumption over time. If engines maintain their internal tolerances significantly longer, those services would become far less common. A $2 solution that interrupts wear at the molecular level is not something that fits easily into that system. Now, look at the oil additive market. Hundreds of products: friction reducers, wear protectants, performance enhancers. Most of them rely on modifying oil behavior, improving viscosity stability, adding detergents, enhancing film strength. But very few actually introduce a true secondary lubrication mechanism. MOS2 does. It doesn't just support oil, it replaces part of oil's role under critical conditions, and that's why it matters. Here is exactly how it's used. During a normal oil change, with fresh oil already in the engine, you add molybdenum disulfide additive, typically around 5% of total oil volume. So if your engine takes 5 liters of oil, you add approximately 200 to 250 milliliters. That's it. No special tools, no modifications, no changes to driving behavior required. Once added, the engine is simply run as normal. As the oil circulates, MOS2 particles are distributed throughout the system. They begin bonding to metal surfaces: crankshaft journals, bearings, cylinder walls, valve train components. Within a relatively short operating period, a stable layer forms. From that point forward, protection is no longer dependent on oil alone. Even if oil film is momentarily compromised, the bonded layer remains. Fleet studies and oil analysis reports have shown consistent patterns when molybdenum-based lubrication is used: reduced friction, lower wear metal content in used oil, more stable compression over time, engines maintaining performance characteristics well beyond expected service life. Taxi fleets and high-mileage operators in parts of Asia have documented engines exceeding 400,000 miles without major internal work. Meanwhile, identical engines operating without this additional protection follow the expected wear curve: gradual degradation, increasing internal friction, loss of efficiency, eventual failure. Now, this is important. This is not a miracle fix. It will not repair a damaged engine. It will not reverse severe wear or mechanical failure. But it can significantly slow the process that leads to those conditions, and in many cases, extend engine life far beyond what is considered normal. Your engine wasn't designed to wear out quickly. It was designed under the assumption that it would operate with consistent protection. But in real-world conditions, that protection is incomplete. Oil alone is not always enough. Japanese engineers didn't create a secret engine. They addressed a limitation in lubrication: